So we've seen the definition of describing function. It is the ratio of, it's a complex ratio of the fundamental component of the nonlinear element and the input sinusoid. So this is the describing function. So it works out to be 1 over a multiplied with the complex number b1 plus ja1. So we have a nonlinear element and its describing function representation this way. So nonlinear element becomes the describing function. It takes a sin omega t as input and m sin omega t plus phi is the output. This is the describing function representation of the nonlinear element. So there are methods of computing the describing function, and the methods are analytical calculation, numerical integration, or experimental evaluation. Let's look at an example. We compute the describing function of a hardening spring. So the W in this case is given by x plus x cubed by 2. We let x as a sin omega t. So the output of course will be a sin omega t plus a cubed sin omega t cubed over 2. And this can be expanded into Fourier series, and the fundamental being these terms, in which a1 and b1 can be computed. By the assumptions and the definition of Fourier coefficients, we have a1 is 0 and b1 works out to be this quantity a1 plus 3/8 a cubed. So the fundamental w1 is this multiplied with sin omega t. So the describing function is this divided by the amplitude of the input sinusoid. So the describing function is 1 plus 3/8 a squared. So this is a block diagram of our control system. We can have sensors, actuators, and controllers, plant. Let's look at certain types of nonlinearities which frequently occur in our daily application of control systems. We have these are normally incidental nonlinearities. We have the saturation nonlinearity, which is from which we derive the on-off nonlinearity. We see the region where the left half is left saturation is becoming right saturation over a linear zone. So when the linear zone is 0, it becomes a step type on-off function. Otherwise, it's a saturation type nonlinearity. This is the dead zone nonlinearity. There is a dead zone where the actuation is not having any output. So the nonlinearity suppresses the value of input in this range to 0. So that's why the region is a dead zone. This is a hysteresis. There are two engaging gears. Hysteresis occurs when the gears age or when there is a defect in the teeth of the gear. So here the gears are shown to have a backlash. So because of some wear or some kind of problem in the gears are not engaging at this location. So for the time the driven gear, this is the driving gear. When the driving gear is rotating, there is a play. There is a region where the driving gear is not driving the driven gear, and that region is precisely the place where they are not engaging. This normally happens when the gears have worn out. So when backlash occurs, there is a backlash nonlinearity, which is a hysteresis. So in one direction, you have the lower part active. In the reverse direction, the other segment of the loop is active. So that's why this backlash causes a hysteresis type of nonlinearity. So in the forward direction, you have D, E, A, B, and forward to the right. And the reverse direction, we have B, C, minus B, D, and so on. So the two loops are different for the forward and the reverse passes of the input. Now let's look at the procedure for computing the describing function. We show the saturation nonlinearity and describe the steps for computing the describing function. So we have the saturation nonlinearity here. So the input of a sin omega t must be given to the nonlinearity, and the output of the saturation must be visualized, drawn, and then the describing function definition is applied over the Fourier series expansion of this output of the nonlinearity and then taking the first harmonic. Those assumptions apply. The describing function is computed over those assumptions already described. So here we look at the saturation example. So A sin omega t is here. The omega t's axis is vertically shown. Actually, the axes are tilted so that the graphical procedure for drawing the output is clear. So A sin omega t is drawn this way. Omega t is along that axis. Xt is along this axis. The W and X are here for the nonlinear part. And for the output of nonlinearity, we have omega t on x-axis and wt on the y-axis. So K is the slope of this line, and A is the point where the saturation onsets. So beyond this, the saturation nonlinearity is active. So from 0 to A, it is linearly active. So we take some point on this axis and then look at the value of x, and then we project it upward to the nonlinearity and take the output from the action of the nonlinearity. So this is how the nonlinearity looks. It may be seen that at gamma is precisely the value of t omega, where the xt just reaches the saturation point. So beyond this point, that is when between gamma and pi by 2 minus gamma, the saturation is active. So for that region, it is the output is horizontal. So from the values shown on these graphs, we can tell how the graph is constructed. So this is the saturated output here. This is the unsaturated output, the dots. So that is the actual sinusoid. The saturated output is shown in the dark line here in the output graph. So we use the output graph and its values. Its piecewise definition is used for constructing the describing function. So this is our piecewise definition by using the graphical procedure we just showed. Gamma is sine inverse of A by A. So when we apply the definition of the Fourier coefficients and the describing function, it works out to be, the B1 works out to be this quantity. We have used the values from the piecewise definition of the output of the nonlinearity. So the 0 to gamma to pi by 2 are taken from the piecewise definition of the nonlinearity, and the B1 works out to be this function. So the describing function, therefore, is B1 by A. The B1 must be divided with the amplitude of the input sinusoid. So this is our describing function for the saturation type nonlinearity. So if you look at a graph of this nonlinearity against A over A, capital A over small a, we have the following features. So the graph is shown here. So this is the graph. There's a linear range and it becomes curved after the linear range. So we're plotting A over A on the x-axis and Na by K. K is the slope of the saturation nonlinearity that is plotted on the y-axis. So the properties are here. Na equals K if the input amplitude is in the linear range. Na decreases as the input amplitude increases. There is no phase shift. There is no phase shift in the saturation type nonlinearity. So this is the graph of the saturation type nonlinearities describing function. So as a special case of the saturation nonlinearity, this is our saturation. So we said that when the K is vertical, this line is vertical, it becomes an on-off nonlinearity. So we can get the describing function for the on-off nonlinearity as a particular case of the describing function of the saturation nonlinearity. So which may be obtained by this formula which we just computed and putting the condition on K. So this corresponds to shrinking the linear range of the saturation function to 0. That is, A goes to 0, K goes to infinity, but K into A is a constant. K into A is constant. So K into A is here, so that is a constant. It's a constant. So applying these conditions and taking the limit, we have describing function for the relay type nonlinearity, that is on-off nonlinearity, or relay type nonlinearity is 4m by pi a. So if I draw the graph of saturation on-off type nonlinearity, you have instant saturation or relay type nonlinearity is here, and its describing function is here. So unlike the saturation where there was a slope k which was finite, k was finite, we had a horizontal line there, if you remember. There's a horizontal line here, linear range, but there is no the horizontal line here. So this goes to infinity as a goes to 0. So this is the describing function for saturation type